This lecture is about the basics of experimental design. You'll see a lot more about this topic in other courses like inference and prediction, but I thought I'd just give you a little bit of the basics so you can get started. So why should you care about experimental design? I'm going to use an example to illustrate why you should. This is an example that actually comes from my area of research. So this is an area where they use genomic information, so information about your genome, to predict what kind of chemotherapy you might respond to best. This is an incredibly exciting result because it would open the door for all sorts of personalized medicine within cancer therapeutics. Unfortunately, they actually performed a very flawed study design and a very flawed statistical analysis, which was pointed out later in this paper. Even more unfortunately, the study had already been ongoing for a long time, and they had actually started clinical trials where they were using those predictions that they had developed in the earlier study to decide what chemotherapies people should get. This was causing all sorts of problems for people because they had performed a poor analysis. So this ultimately led to a lawsuit from the people that were enrolled in the clinical trial against the original investigators who developed the predictive model. This illustrates how a very exciting result can lead you astray if you're not very careful about experimental design and analysis. The first thing to be aware of when performing any sort of experimental design or data science project is to care about the analysis plan. This is actually a published paper where, believe it or not, in the abstract of the published paper, it says insert statistical method here, because the person who was writing the paper didn't know what the statistical method was. It's critically important that you pay attention to all aspects of the design and analysis of a study so that everything from the data cleaning to the data analysis to the reporting, so that you don't end up, first of all, in silly, embarrassing situations like this, but more importantly, so that you're aware of what are the key issues in the study design that could trip you up. Regardless of what your study you're doing, you need a plan for data and code sharing. You all now have GitHub accounts that you've developed either through this course or previously to the course, so that's a good place to share your code. If you want to share your data for very small amounts, you can share it on GitHub. Larger amounts might go on a site like Figshare, where you can share scientific data and also other kinds of data with other people. But you might also need a larger data sharing plan if your data are much more unwieldy or large and can't be shared on these websites. If you don't have a data sharing plan, can I recommend mine? The Leak Group has developed a guide to data sharing that you can find at this website here that outlines all the steps that are involved in taking a raw data set and making it available to other people. So the first thing that you need to do when you're actually performing the experiment is formulate your question in advance. So the key component of data science, as we're going to define it for the purposes of this course track, is that it's actually a scientific discipline. And a scientific discipline requires that you're answering a specific question when you're using data. So here's one example of that. This is actually a study that was performed by Barack Obama when he was running for re-election for the United States presidency. What they did was they compared two versions of a website, whether they were going to change the text on the website and see if it would improve donations. So the experiment was to randomly show visitors one version or the other of the website, measure how much they donate, and then determine which is better. This brings us to the key idea of a large component of data science, which is statistical inference. They wouldn't want to show the website to every single person because it would be expensive to run that experiment. So the population of people is all possible donors in the United States, all possible people that might go to Barack Obama's website and donate. They might select some small subset of those with a probability argument to decide to show them one version or the other of the website. This would result in a sample, a much smaller number of people that had observed the data or had observed the websites and had decided whether to donate or not. They would then calculate descriptive statistics, say the total number of donations that they got over a certain number of visits, or the average amount of donations they got over a certain number of visits. And then they would use inferential statistics to try to decide if the statistics that they calculated on this small sample would play out in the same way if they applied it to the large population of all people that might come to the website. So here is one scenario. Suppose that the data work they collected hypothetically turned out this way. There were two versions of the website. There was the donate version and there was the sign up version. And so what they could do is they could say for every 1,000 visitors, what was the total number of dollars that were donated? So if they did that over or the average number of dollars donated. So for 1,000 visits, you might get about $6,000 on average over a course of a week. And so suppose you ran that experiment 3 different times, you might get observations of varying different amounts of dollars that you would observe for the donate case and for the sign up version of the website. So what you see here is that the average number of donations may be more or less the same, or it might be slightly different, but it's very hard to tell because in each of the different experiments, you get a highly variable answer under both of the different versions of the website. Here's another hypothetical case. Suppose in this case, you got a very slightly smaller number of dollars donated when you showed the sign-up version than you did the donate version. Here, the variability is much smaller, so you can tell for sure that the donate version gives you more money. You might implement the donate version, but it's not clear that that will give you a huge benefit. The much bigger benefit comes when you run the same experiment and the donate version has small variability and the sign-up version has small variability in the total number of dollars donated, but there's a large difference between the amount that people donated when they saw the donate sign and the amount they donated when they saw the sign-up sign. So this overwhelms the variability that they saw in the experiment, and so it's very interesting for them and would suggest that they should only show the donate version of the website to people that came to visit. Another important issue is the issue of confounding. So suppose in a particular study that you measured both shoe size and literacy. And suppose that you were looking for correlations between shoe size and literacy. You might actually observe quite a few of these correlations because people with small shoes tend to have less literacy. But what you might be missing is that age is actually the variable that's causing this relationship. When you're very young, say a baby, you have a very small shoe size. You also have a very small literacy. As you get older, you get a larger shoe size and a larger literacy, so that the variable age is actually a confounder for the relationship between shoe size and literacy, which might be very, very small once you account for age. So if you only measure shoe size and literacy, you might be led astray if you observe a correlation between these two variables. This is what's called confounding. So it's paying attention to what are the other variables that might be causing a relationship. This plays out all the time in lots of different studies. So here's one example. This is actually from a possibly serious paper in the New England Journal of Medicine, where they plotted chocolate consumption in kilograms per year per capita versus the Nobel laureates per 10 million in the population. And they observed that there's a relationship between these two variables. So what could be going on here? There's lots of reasons why you might consume more chocolate and have more Nobel Prize winners. For example, your country might have better education system if they have more money, and so they would have more Nobel laureates. And if they have more money per capita, they would also probably consume more chocolate per capita. And so there's one reason of many reasons why this observed correlation may not be an actual relationship that is due to a scientific relationship between chocolate consumption and Nobel laureates per capita. This is sometimes called spurious correlation, and it's also why you often hear the phrase correlation is not causation. Even if you observe that two variables are correlated with each other, you have to prove to yourself that they're not correlated because of some other variables we didn't measure. So there's some ways that you can deal with potential confounders. So one way is you can fix a bunch of variables. For example, in the case where you're considering websites for Obama 2012, you can fix Obama 2012 on all the websites. There should be a 2 there. And then that way, that variable doesn't change no matter what the text is that you're showing people. So you fix that variable. So it can't be a confounder. Another way is that you could stratify. So suppose you have 2 website colors and you want to try out both of those website colors with both phrases and you want to know which phrase works better. Then what you can do is use both phrases equally on both colors. That way you've stratified your sample so you have both website colors used equally with both phrases. If you can't do either of the other 2 things, if you can't fix a variable or stratify it, then what you can do is randomize it. And so what we mean by randomization is that you need to be able to use a computer program or flip a coin in order to randomly assign people to groups. Why does this help? So suppose that there's a particular study that we're performing, and suppose that there are 10 experimental units that look like this. So suppose there's a confounding variable, and lower values of that confounding variable correspond to lighter colors, and higher values of the confounding variable correspond to darker colors. So you have these experimental units, and suppose they're ordered by the values of the confounding variable, and suppose we were silly enough to provide one treatment applied to all the people that have a high value of the confounding variable, and another treatment to all the people that have a low value of the confounding variable, then it would be impossible to distinguish whether any difference we saw was due to differences in treatment or due to differences in the confounding variable. But if we randomly assign the treatment, then some of the people that get the green treatment will have low values of the confounding variable, and some will have high values. And so since that will be balanced, we'll be able to determine whether the difference will be determined that the difference in treatment is what we're actually observing in the outcome. So for a prediction study, you actually have slightly different issues that come up from the inferential case. So again, you might have a population of individuals, and you might not be able to collect the data on all those individuals, but you want to predict something about them. So for example, we might get individuals that come in and we measure something about their genome, and we want to predict whether they should whether they're going to respond to chemotherapy or not. So what we do is we collect these individuals, and we might collect observations from people that did respond to chemotherapy and did not respond to chemotherapy. And then what we want to do is build a predictive function so that if we get a new individual, we can predict whether they're going to respond to chemotherapy up here as an orange person or not respond down here as a green person. So the idea here is that we still need to deal with probability and sampling and potential confounding variables because when we're building this prediction function, we want it to be highly accurate. Another issue that comes up is that prediction is slightly more challenging than inference. So for example, if you look at these two populations, the population for the light gray curve has a mean value about here, and the population for the dark gray curve has a mean value about here, if you look at the distribution of observations from these two populations. And so what you can see is there's a difference in the mean values of these two populations. But if I tell you, for example, that I've observed a value that comes, say, right here, it's very difficult to know which of these two populations it came from because it's relatively likely that it came from the light gray population, but it's also relatively likely that it came from the dark gray population. So it's very difficult to tell the difference. For prediction, you actually need the distributions to be a little bit more separated. So these two distributions also have a different mean, but now they're far enough apart based on their variability that if I give you an observation that lands right about here, you know it probably came from the dark gray population, where if I give you an observation here, it probably came from the light gray population. So it's important to pay attention to the relative size of effects when considering prediction versus inference. For prediction, there are several key quantities that we need to be aware of. So the first set of key quantities are the positive and negative statuses. So for example, this comes from a test from a medical testing scenario. So you can have, suppose you can either have a disease or not have a disease. So plus means you have the disease and minus means you don't have the disease. And you have a test to determine whether you have that disease or not. And the plus means the test was positive, and a negative means the test was negative. So if you have the disease and you test positive, then you're a true positive. If you do not have the disease and you test positive, that's a false positive. If you have the disease but don't test positive, that's a false negative. And if you don't have the disease and you test negative, that's a true negative. Some quantities that you need to pay attention to are the probability you have a positive test given you have disease, that's sensitivity. The probability you have a negative test given you have no disease, that's specificity. The probability you have disease given you have a positive test, this is probably what you care about if you come into the clinic. So if I tell you that you have a positive test, then you want to know what's the probability that you have disease. Similarly, if I tell you if you have a negative test, you might want to know what's the probability that you have disease. Accuracy is just the probability that you were correct in the outcome, regardless of whether you are positive or negative. Another key component of paying attention to big data and data science is being aware of data dredging. So suppose you want to consider something silly, like jelly beans cause acne. This comes from an XKCD cartoon. So scientists could investigate, and they find out that jelly beans aren't related to causing accuracy. causing acne. So then what they say, well, that settles that, but you could try to change your hypothesis. You could say, oh, well, actually it's just purple jelly beans that cause acne. No, it's brown jelly beans that cause acne. No, it's pink jelly beans. And you could keep going and going and going until you found a result that you liked, and you come up with good news. Green jelly beans are linked to acne. But this, of course, ignores the fact that you tried a whole bunch of different things first. So one thing that you have to pay attention to when dealing with big data or with any data science problem is being aware of the problem of data dredging. So in summary, good experiments have replication so that you can measure variability. They measure that variability and compare it to the signal that they're looking for, and they generalize to the problem that you care about. Also important, good experiments are transparent in both their code and their data. Prediction is not inference, and both can be important, but it depends on what your application is. Also, in any data science problem, you need to be aware of data dredging. The other important issues with experimental design will be covered in later classes.